All right, a couple of people asked about theorem 3.6, where we're showing that this set ZE is a subring of F and is isomorphic to the ring Z plus times. If I went through the whole thing, it would be quite a long process. So I'm going to go through some of the highlights. I'm not sure if I'm going to type everything up though. So we'll just see. I'll give myself 30 minutes and then see where we're at. All right, so let F be an ordered field with multiplicative identity E. Then the set ZE equals NE is a subring of F and is isomorphic to the ring Z plus times. So there's really, when I first read this, I see that there are two things that we have to prove. First, we have to prove that ZE is a subring. And then we also have to prove that it's isomorphic to Z plus times. And then let's recall, before I get even start, like what is NE? NE equals E plus E plus E n times. This is when n is positive. If it, n, let's just do 0e. 0e equals theta. So theta is the additive identity. And then ne equals negative e plus dot 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 plus negative e when n is negative. So negative n times. All right, we want to show that that's a subring. All right, so subring, we're going to choose A and B in ZE, and then show what A plus negative B is in ZE, and then A times B is in ZE. So, all right, so A is going to equal, if we're in ZE, A is going to be M times E, and B is going to be N times E for some integers M and N. Let's see, note. All right, so let's look at, so A plus negative B is, let's see, that's going to be ME plus negative N. Negative NE. And negative NE is, there are two ways to think about it. This is one of the homework problems. You can think about it as negative, well, here, maybe up here. So negative NE is the same as N times negative E is the same as negative N times E. All right, these are all the same. All right, so how do we want to, I feel like we have to think about, right, because we have different definitions based on if M and N are positive or negative or 0. Maybe we'll just say if N or M are 0, then the result, maybe say that it is clear, then it is, right, because there's, right, we could go through these cases. If M is 0, then blah, and then if N is 0, then blah, and they're both like very similar and pretty trivial. So I'm just Like, I don't really want to think about that too much. And it's clear that A plus negative B is in ZE. All right, so now maybe if they're both positive, if N and M are both positive, now there's a little work to do, then A plus negative B is ME plus, I'm going to do that version of negative NE, because then, right, since now N and M are both positive, then this is pretty straightforward. So then this is just E plus dot 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 plus E plus negative E plus negative E plus dot 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 plus negative E. This is M times, and this is N times, and then and then you just say this is in ZE since, well, let's see. I was going to say, hey, this is in ZE because ZE is closed, but we're trying to like prove that it's closed. I think it's clearly an F. Yeah, this depends on the relationship between M and N. Oh, maybe this is... Oh, this makes me think I want to be able to say, like, you know, without loss of generality, M is less than N. Otherwise, I have a whole bunch of cases to work through that I don't want to work through. Yeah, so maybe let's just say, like right up here, like without loss of generality, M is less than N. Oh, I actually want to say the other way. I want to say M is greater than N. Yes. Oh yeah, I think it's going to be hard either way. I'm right. I'm thinking like, hey, I want to, like, you know, count these up, and I want there to be more of these things, more E's over here than negative E's over here. Well, it actually doesn't matter. Maybe I just need to think about the difference. Yeah, maybe the difference is important. The difference of M and N. What would this say? If N is less than M, then M minus N is positive. Yeah, let's stick with that. Let's stick with this. Let's stick with M is greater than N. So then what does that mean? That means that, okay, so then this is, right, so since M is greater than N, we do like associativity and stuff. We do associativity, and like we can, you know, cancel some of these out. Like that one's going to cancel with that one. That one will, I guess, simplify with that one, so on and so forth. So we get E plus E. I get, oh man, now it's got to be greater than or equal to, greater than or equal to, greater than or equal to, plus dot dot dot, plus E, and this is going to be M minus N times, which is going to be M minus N times E, which is in ZE since, oops, M minus N is in Z. I feel like there's like a lemma I need to write. Right, I want to say, like, this is all fine and dandy, but I want to say, like, yeah, no, this is essentially what I'm proving. Well, yeah, that's essentially what I'm doing here. All right, and I want this to be true for any value of M and N. Maybe I just prove that lemma first, and that would make everything nicer. Oh, maybe we do that. That would make this pretty slick. It'd be a lot of work though, because you'd have to think about M and N being, yeah. We're essentially just proving that lemma right here. All right, okay, whatever. We're gonna prove that lemma. All right, if they're both positive, then we get this result. If they're both negative, if N and M are both negative. Yeah, so then note that this only applies when they're both positive, by the way. If they're both negative, right, if they're both negative and N is down here and M is up here, so N is less than M, then, oh no, that still works. Oh yeah, duh. Then we still get, yeah, oh that's, okay, yeah, that's always true. Oh wait, so it doesn't matter. Oh, it does matter about the definition. Yes, it matters about these definitions. Okay, that's why we had split it up with positive and negative. Okay, if M and N are both negative, then A plus negative B is ME plus negative N. No, I think we want to do, yeah, no, it doesn't really matter. And negative E. Right, so now we have a different definition. So negative E plus dot 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 plus negative E. How many times? Negative M times. And then now since N is negative, we have negative E. Yeah, so this will be negative E plus negative E plus negative E negative N times. All right, so we have negative E plus negative E plus negative E plus, and this is E plus E plus E. Oh, it's getting pretty lazy with that. Negative M times negative N times. All right, now what do we know about negative M? So if N is less than M, then negative M is less than negative N. Right, they're both positive, so negative N plus M is positive. Right, right, how many, I'm just trying to count how many e's are left. Oh yeah, negative n, oh yeah. So these are gonna cancel out. A bunch of them are gonna cancel out. But there are more of these than there are of these, because negative n is bigger than negative m. So how many are left in particular? Negative m plus n. This is going to be like a positive number. Okay, that's nice. Let's move this stuff over here. Right, so this is going to be e plus e plus e. How many? Negative n plus m times, which is negative n plus m times e, and negative m plus m is in z. So the a plus negative b is in ze. Okay, great. So if they're both positive, we're in there. If they're both negative, we're in there. And then if one is positive and one is negative, it's a similar argument. I don't really want to go through those details. Okay, so then the product, let's just do a product just to convince ourselves. A times B is, what's A? ME is ME times NE, so it's ME times E. Let's assume they're both positive. E plus E plus so that's N times, and then we distribute. So we have M, right? ME times E. I mean, it's just ME plus ME plus ME N times, which is E plus dot 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 plus E. Right, that's the first one. And then E plus E, that's the second one. And then you got a whole bunch more. E plus E. That's that one. So then we have, each of these are M copies of E. And there are a total of N. So how many total E's are there? There are M times N E's equals E plus E plus E N times M times, which is NM E. And M is an integer, so A times B is in ZE. All right, so that's right. And then there are more cases when M and N are negative, and then when one's negative and one's positive. But it's the same idea where we just unpack all these definitions and then we count how many things we have left. right? So this is the idea. This is the scratch work to show that it's a subring. That's just the first part. I don't know if taking a picture of this is even useful, but we will. All right. Now we want to show that we're isomorphic. So we want to show that Z plus times is isomorphic to ZE O plus O times as rings. So essentially we need to find phi either from Z to ZE or ZE to Z. Phi is 1-to-1 and onto, and then phi of M plus N equals phi of M plus phi of N, and then phi of M times N is phi of M times phi of N. So we're going to define, so phi is going to be, let's define phi of N to equal NE. It's pretty straightforward. Right, we start in Z and we end in ZE. Right, I think it's pretty clear that we're 1-to-1 and onto. Right, let X be in ZE, then X equals KE for some integer K, thus phi of K equals KE equals X. So there we're onto. And then 1-to-1, assume phi of M equals phi of N, then ME equals NE. And then there was a theorem that says if M and N are distinct, then M, where is that theorem? Here it is. Hold on, let me bring it in quick. Right, if those two integers are distinct, then NF and MF is distinct, and if we use a contrapositive, that means if they're the same, then NF and MF are the same. And then this implies M equals N, so that is 1-to-1. All right. Okay, so we're 1-to-1, we're on to. Now phi of M plus N equals phi of M plus phi of N. All right. Phi of, let's go. So phi of M plus N equals M plus N E. And then if, again, this is going to break down to M and N positive and negative. It's going to be a whole bunch of cases. I would just pick one case to prove, right? So what are the cases? M greater than 0, n greater than 0, m greater than 0, n less than 0, m less than 0, m greater than 0, and then both less than 0. And all those cases are going to be very similar. So I'm just going to pick one to show, and it works. Let's pick like, if they're both positive, that one's pretty straightforward. So I'll pick one that's like maybe less straightforward. Let's do this one. M is negative and n is positive. And again, this is now gonna, so, all right. M is less than 0 and n is greater than 0. Oh yeah, this is hard because now, right, I'm looking at m plus n, and it depends on if m plus n is positive or negative. We want it to be phi m plus phi n. Well, let's just use, okay, so now, right, working like this is kind of hard. Let's start at the other side. Let's do phi of m plus phi of n. So that's going to be me, plus ne, which is, right, by definition, since m is negative, it's going to be negative e plus negative e, plus negative e plus e plus e plus e, and that's going to be negative m times, and this is going to be n times now I'm just trying to think about, I'm trying to count. Yeah, now this is going to split into two cases. Right? Negative m plus n is less than 0. No. M plus n less than 0, or m plus n greater than 0. So if m, let's do the one on the right, if it's positive, then that means that there are more e's than negative e's. So it's going to be, we're going to get e plus plus e, m plus n times. And then here, this would mean there's more negative e's than e's. So we're going to get negative e plus negative e plus negative e plus negative e m plus n times. So this is pretty clearly m plus n e, which is phi of m plus n. So that works out great. Right, because remember, we're trying to show this. This one is weird. M plus n times m plus n is negative. Right, I'm just trying to think about the definition. Like, I want to say now that this is just, but I don't know. It's not making sense right off the bat. I want to say that this is m plus n. What do I want to say? Yeah, I want to say that's m plus ne. But that doesn't, I feel like that doesn't make sense, right? Isn't that really m plus n negative e? What's going on here? Did I do this right? M is negative and n is positive. M is negative and n is positive. So negative m is positive. So if this is negative, yeah, this doesn't seem right. Oh, okay. I see. I did this wrong. Okay. I think I screwed up this definition. All right, I was trying to do two things at once. Oh, no, that's right. If m is that right? M times e, if m is negative, is, yeah, that should be negative e plus negative e plus negative e. Negative m times. Is that the definition? Hold on. What's the definition? Yeah, that's the definition. That's the right definition. But why is it not working out? M is negative. N is positive. Yeah. All right, so then I'm just gonna restart. Oops. All right, I got stuck, and I just need to just restart. So we want to show phi of m plus n is phi of m plus phi, O plus phi of n, and we're working through the case where m is less than 0 and n is greater than 0. And we're in the case where, let's just restart. Don't even look at the last one. All right. So phi of m plus phi of n is me, by definition, plus ne. If m is negative, then it's negative e plus negative e plus negative e plus e plus e plus plus e. How many times? Negative m times. Negative m times. How many times? That is n times. All right. Right? This is right. So now we have two cases. If n, I'm going to think about it differently. If n is greater than negative m, then we get a bunch of positive e's. E plus e plus e. How many of these do we have? Right, maybe let's pick let's pick some specific numbers. So 7 and 4. So then that means that m is negative 4. So then we're going to have 7 plus negative 4. We'll have 3 of those left. Yeah, that's what I thought. N plus m times. So that is n plus m e, which is phi of m plus n. Oops. M plus n. Let's be consistent. All right, so if n is less than negative m, let's say n is 5 and negative n is 8, then we have negative e plus negative e plus negative e. Right, there should be 3 of them. Is that right? Because we have so now how do we write the number 3 in terms of m and n? It's negative. Yeah, it's negative m plus n times. Oh, yeah. It's negative m plus n because m plus n is negative. So it's negative n plus n with the negative e. That is, yes, that is, oh, yeah, great. M plus n e. I see. Yeah, so what was happening... This was wrong before. This was supposed to be negative m plus n times. So then we'd have negative m plus n negative e, which is the same as m plus n e. That's what I was missing. Okay, great. And this is why you just restart. Okay, which is phi of m plus n. Right? Yes. Okay, great. All right. So now we formalize it, which essentially just means we, type all this stuff up. Now, if we wanted to do every single case, it would be like it'd be a 4-page proof because we got all these different types of M and N. Oh, okay, let me quick. All right, this is the plus. Let's see, can we do the times quickly? All right, I'll just try to do the ideas for the times. Goal, phi of M times N is equal to phi of M times phi of N. Okay, let's start here. It's going to be M E times NE. If they're both positive, then, right, we kind of did that. We did that before. Right, this is essentially the case where they're both positive. Right, and then we get N times M. So that's the case where they're both positive. If they're both negative, very similar. So, okay, one positive, one negative. M is negative, and it's positive. This should be the hardest case. So we get negative E. No, let's do this. It'll be M E times, so we're going to use distribution E plus E plus E, N times, and then that's going to be ME plus, we distribute, ME plus ME plus ME, still N times. So then we'll get negative E plus negative E plus negative E. Right, that's that one. Plus dot 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 plus negative E plus negative E plus negative E. That's the last one. Each one of these has negative M copies of negative E, and there are an overall N copies. So how many negative E's do we have? We have N times, if we drop all the parentheses and just add up all these negative E's, all right, add up all of them. Now we're just counting. How many negative E's do we have? We have N times negative M negative E's, which is the same as negative M times N negative E's, which is M times N E, which is phi of M N. Phi of M. Let's do times. Times. Here we go. So that's essentially, that's the hardest, probably the hardest case of the isomorphic structure. I don't know if these pictures are going to be useful. I forgot what I took pictures of already. Well, let's just... All right, let's take a few pictures. This one. And then this was an idea over here. And then we had some ideas over here. And then an idea here. And an idea. Oh, we can't see that. Idea here. Right, notice, right, this last one went quick because of the mistake earlier. All right, this transition here, that's where I got hung up with last time when we got stuck. But because I got stuck and then got unstuck, this transition here was pretty quick. All right, that's it. That was a long one. I didn't even get to the formalization.